There's a joke. To those who haven't studied physics, the world seems full of magic. And in this joke, there's a large grain of truth, especially when it comes to one branch of physics, namely optics. Indeed, many phenomena described by optics, such as rainbows, halos in all their variety, mirages, and the like, were once explained by various kinds of wonders. And the most interesting thing here is that, essentially, most of these optical wonders are connected with just one phenomenon: the fact that light, when passing from one medium to another, has the property of refraction, changing the angle of propagation, as well as with its special case when this angle depends on the wavelength of the incident light, that is, with the phenomenon known as dispersion. And if we truly want to provide a scientific explanation for various optical wonders, then we must, in general, understand why light propagates in different media in this way. In principle, this matter is taught in the school course of linear optics, where we are explained that it is related to the fact that the speed of light propagation in different transparent media is different. We are even given the so-called Snell's law, which states that the ratio of the angle of incidence to the angle of refraction will be equal to the ratio of the speeds of light propagation in the media. Alternatively, if we introduce the so-called refractive index, equal to the ratio of the speed of light in the medium to its speed in vacuum, then Snell's law will be rewritten in this form. Snell's law can be easily explained with the help of an intuitive mechanical analogy. Let's imagine a tractor driving on asphalt approaching a boundary with a less suitable surface, say a plowed field. Since the tractor is moving at an angle to the boundary of the two surfaces, at the moment when one of its wheels has already entered the field, the other will still be on the asphalt, meaning the axes of the tractor's wheels will start moving at different speeds, thus inevitably turning the tractor at some angle. Like any analogy, this analogy is not flawless, but it provides a notion of what's happening. For those interested in a more rigorous explanation, I suggest conducting it based on Fermat's principle, which quite plausibly states that light propagates in such a way as to cover the distance between points in minimal time. Let's assume that in our case, light propagates in such a way as to reach from point A to point B, between which lies the boundary of two media, and our task is to determine its trajectory, i.e., essentially to understand where point X will be, where the light will hit the surface of the boundary. Obviously, in the first medium, light will travel a distance L1 equal to the square root of the sum of a squared and x squared. In the second medium, it will travel a distance L2 equal to the square root of the sum of b squared, the depth of the second layer, and the square of the quantity d minus x. Accordingly, the total time it will take to cover this path will be L1 divided by v1, i.e., the speed of light in the first medium, plus L2 divided by v2, i.e., the speed of light in the second medium. Since we need to determine the position of point X, at which the time spent on the journey will be minimal, we must do a completely standard thing, which is customary in mathematics for determining the minimum of a function. Take the derivative of this function, that is, of our expression for time, with respect to x, and set it equal to 0. This derivative will be written in this way, and setting it equal to 0, we obtain this condition for the minimum time of light propagation along the path from point A to point B. Now we need to pay attention to the fact that this thing here is nothing but the sine of the angle of incidence of light on the boundary of the media, and this is the sine of the angle of refraction after passing through this boundary. Then our condition for the minimum will be rewritten in this way, from which we easily and naturally derive our Snell's law. It is possible, of course, to derive it differently, for example, through Huygens Fresnel principle, and usually in the school physics course, it is done that way. But personally, I prefer this method because it is purely mathematical, and equations, as we know, are smarter than us. And in general, physicists need mathematics to simplify their lives. All this, I repeat, is completely within the scope of the school course of linear optics. And it is considered that by explaining this, we have basically explained the law of refraction of light. However, one little annoying moment always remained incomprehensible to me. Why does it turn out that light propagates at one speed in some media and at another in others? And why is this speed different for different wavelengths, explaining the mass of beautiful optical effects, including rainbows. Answering this question is slightly more complicated than deriving Snell's formula, and probably that's why it's not answered in the school physics course. But if we really want to understand why optics works exactly like this, then we still need to answer it, and that's what we're going to do now. To understand why light propagates in a substance at different speeds, we need to first recall what substances consist of and what light is. So light, I remind you, is an electromagnetic wave, that is, a disturbance of electric and magnetic fields propagating through space. The magnetic component of this wave will interest us less in this video. We have a separate video on how it affects the substance through which light propagates. Today, we will focus on the electric component of the wave. Its presence means that a time-varying electric field is present in the wavefront, the intensity of which periodically changes from E0 to minus E0, where E0 is called the amplitude of the wave. It is this magnitude that roughly determines the brightness of the light we observe. Now let's see how the substance through which light passes will react to the passage of such a disturbance of the electromagnetic field. As a rule, the substance as a whole is electrically neutral. That is, it has zero electrical charge. However, this substance is composed of charged particles of one kind or another. These can be negatively charged electrons and positively charged atomic nuclei, positive and negative ions of ionic crystals or electrolytes, positively and negatively charged poles of dipole molecules, and so on. And so each such charged particle of the substance will be subjected to an electric force in the field of the electromagnetic wave, equal to the product of the magnitude of the wave field by the charge of this particle. And under the action of this force, particles will be displaced in a certain way, generally oscillating around their initial position. However, the force caused by the wave field is not the only one that affects these particles. As we discussed earlier, in most cases, in a substance, we deal with bound charged particles, that is, particles that are parts of more complex complexes, whether it be an atom, a molecule, or a whole crystalline lattice. Within these complexes, particles are in a state of stable mechanical equilibrium. That is, if we displace a particle from the equilibrium position, for example, by the action of an electric field of the wave, a force arises that tends to return it back to the equilibrium position, directed against the displacement. The nature of this force depends on which specific particle in this substance we are talking about. However, for very small displacements, it can be said that this force will be directly proportional to the displacement with some proportionality coefficient k. This is a fairly common approach in physics. The thing is, mathematically, any function can be represented as a power series with some coefficients, and if the values of x, that is, the argument of the function, are small, then with a known degree of accuracy, we can limit ourselves to the first terms of the series, or even just the very first term, as in our case. The rest will also be present, but will be too small, and we can neglect them. This is how, for example, the restoring force acting on a mass attached to a spring looks like if we slightly stretch and compress this spring. And we know what the motion of the mass in such a system will look like. It will undergo oscillatory motion with the cyclic frequency omega 0 equal to the square root of k divided by m. We have a slightly more complicated case. Oscillations occur under the influence not only of the restoring force, but also of an external periodic force, caused by the influence of the electromagnetic field. That is, the total force acting on our charged particle will be determined by the sum, or rather the difference of these forces, since they are directed in different directions. If we recall that acceleration is the second derivative of the coordinate with respect to time, then our equation will be rewritten in this way, and we will get a differential equation from which we can obtain the dependence of the particle's coordinate on time. That is, the equation of motion of this particle under the influence of an external periodic force caused by the electric field of the electromagnetic wave. The solution of the equation will be this thing. That is, under the action of an external field and an internal restoring force, the particle will begin to oscillate with the frequency of the external force and an amplitude depending on the difference between the frequencies of its own oscillations and the frequency of the incident electromagnetic wave. This equation is familiar to us from classical mechanics. It is the so-called equation of forced oscillations. If omega 0 and omega, that is, the natural frequency of oscillations and the frequency of the forcing force, are equal to each other, the amplitude of oscillations by this formula becomes infinite. This is the so-called resonance phenomenon. I think you've heard all these stories about soldiers marching in step across a bridge, causing it to collapse. However, in reality, if you get a mathematical infinity solving a physical equation, it usually means that you have simply gone beyond the applicability of your model. In our case, this is exactly such a case, because we agreed to consider the oscillations of our particle small, but with close natural and external frequencies, this is no longer the case. Therefore, let's not go beyond the scope of our model and assume that the difference between omega and omega 0 is significant. Actually, this is what happens in transparent media, for which it is generally appropriate to speak of the refractive index. So, under the influence of an external electric field, the charged particles of our medium enter into oscillatory motion with the frequency of the incident electromagnetic wave, that is, the incident light, and with such an amplitude. How will this affect the speed of propagation of electromagnetic waves in such a medium? There are two ways to understand this. The first is how it is explained to students in electrodynamics classes. It's a good and beautiful explanation, but it consists almost entirely of mathematics. So I will certainly present it here, but only for reference so that you know how these things are done in physics. And then we will consider another, more understandable explanation with fewer formulas. From Maxwell's equations for the case of an electromagnetic wave, we can obtain this relationship, which is a special case of the so-called wave equation, specifically for an electromagnetic wave. This thing in wave equations is precisely the square of the wave velocity, or rather, the square of the phase velocity. What it is, and how it differs from the ordinary wave velocity, we will discuss a little further. Here, c is the speed of light in vacuum, epsilon is the so-called dielectric permittivity of the medium, and mu is the magnetic permeability. The latter is usually close to 1 for transparent materials, so we can simplify our expression for the speed of light in the medium to this. The dielectric permittivity is equal to this thing, where chi is the so-called dielectric susceptibility, which in turn is recorded like this. Here, P is the polarization of the substance, E is the external electric field. The polarization of the substance is equal to this thing, where N is the number of particles, atoms, molecules, or ions, in the volume of the substance, and P is the so-called electric dipole moment. And this is the product of the charge of the particle by the amount of displacement of this charge from the equilibrium position under the action of the field. And in our case, this displacement is precisely equal to the amplitude of the forced oscillations of the particle under the action of the electric field of the electromagnetic wave. So, having gathered all this together, we get a formula for the speed of light propagation in a medium, and by dividing this expression by the speed of light in vacuum, the formula for the refractive index, the so-called Sellmeier formula. As you can see, the speed of light in the medium, and consequently the refractive index, and therefore the angle at which light propagates in the medium after refraction, depends on the frequency of the incident light. And this is precisely the phenomenon we call dispersion. And since for transparent media, the natural frequency of oscillations is usually significantly higher than the frequency of visible light, then, as a rule, the higher the frequency of the incident light, the higher the refractive index of this light by the medium. That is, if a beam consisting of waves of different frequencies falls on the boundary between media, these rays will refract at different angles. The shorter the wavelength and the higher the frequency, the more the beam will deviate. This is precisely the principle behind the decomposition of color into a spectrum by a prism or, for example, a rainbow. But, as I mentioned earlier, the reasoning we use to derive the Sellmeier formula doesn't give us much in terms of understanding why the medium actually slows down the passing light rays. To correct this omission, let's try to explain the same thing a little differently. So, we have already concluded that under the influence of the electric component of the incident light wave, charged particles of the substance, whatever they may be, enter into oscillatory motion, and we know what accelerated moving charged particles do. They themselves begin to emit electromagnetic radiation. That is, when a light wave passes through a substance, this substance itself, or rather the various charged particles of which it consists, also become sources of light waves. And the resulting wave passing through the substance will be the sum of the original, or incident wave, and the secondary wave created by the oscillating charged particle in the field of the incident wave. By using the equations of electrodynamics, one can calculate the formula for this secondary wave. It will turn out to be like this, where E with a dash is the amplitude of the secondary wave, proportional to the amplitude of the oscillations of the charged particle. And since we agreed to consider that this amplitude for a given type of particle and a given field strength is small, and this is actually the case in transparent bodies, then we can conclude that E with a dash is generally much smaller than E0, i.e. the amplitude of the incident wave, and it is all the greater the closer the resonant frequency of the oscillations of this particle and the frequency of the incident wave. It is worth noting that the secondary wave, as we discussed in one of our previous videos, propagates not only in the same direction as the wave of the incident light, but also, generally, in all directions, including in the opposite direction, that is, away from the boundary of the substance. It is these waves that represent the reflected light falling on the boundary. The amplitude of the reflected light wave will also be equal to E with a dash. And since we know that transparent media reflect only a small part of the incident light flux, for glass, for example, it will be only about 7% when a beam of light falls perpendicular to the plane of the plate. Then we can conclude that our assumption of the smallness of E with a dash compared to E0 was correct. We will return to the reflected light a little later, when we deal with its refraction. So for now, we are only interested in the wave that penetrates into the material. So the equation of oscillations of the total wave, consisting of the incident and secondary waves that have passed into the substance, as we said earlier, is described by this relationship. It can be simplified by factoring out E0 and obtaining this relationship, where E with a dash divided by E0 is a small quantity, the value of which depends on the amplitude of the oscillations of the charged particle, that is, on the difference between the resonant frequency and the frequency of the incident light. If we plot graphs of the incident wave, secondary wave, and total wave for such conditions, we will see a very interesting phenomenon. The total wave for the case of very small e with a dash will essentially represent the original wave, but somewhat shifted. That is, passing by a charged particle, our original wave receives a slight push, as if pushing it back a little. Obviously, as it continues to propagate in the substance and reaches the next particle, the wave will feel another push, reaching the next one, and so on. That is, as the wave propagates in the substance will seemingly push the wave back each time it passes through another layer of substance. And as a result, we will get a situation where the wave will propagate slower, exactly as we discussed earlier. This can also be shown from trigonometric considerations if we recall that the sine of a very small quantity is equal to that quantity itself, and the cosine of a very small quantity is equal to 1. Then we can transform our expression for the total wave in this way, and this is nothing but the expression for the sum of sines. That is, our total wave will turn out to be equal to the original wave, but slightly phase-shifted relative to the original wave. This will be the same push, the phase shift of the original wave, which it will undergo when interacting with each subsequent layer of particles, what will look like a slowing down of the wave when passing through the substance. So we have come to the same conclusion that we previously obtained from purely electrodynamical considerations, but now we have a better visual understanding of this process. If you have been following our reasoning carefully, you may, and ideally should, have a question of this nature. We have considered media in which the resonant frequency of oscillations of charged particles is much higher than the frequency of the incident light. But what if it's the other way around? In this case, The second term in the Sellmeier formula will be less than 0, and the refractive index will become less than 1, which seems to tell us that the speed of light in such a medium will become greater than the speed of light in a vacuum. Does this mean that the wave in such a medium will move at superluminal speed? That is, photons that form our wave will travel faster than when they travel in a vacuum? This is indeed a logical question. And without our second reasoning about the nature of wave slowing in a medium, it would be difficult for us to find a way out of this apparent contradiction. However, now we can do it effortlessly. In fact, above we talked about the so-called phase velocity of an electromagnetic wave in a medium, that is, the speed at which points in space with equal phase of oscillations propagate. And this is not the same as the speed of flight of photons. Roughly speaking, photons will always travel at the same speed, and even in a substance where the refractive index for waves of this length is less than 1. That is, the area inside the substance to which the wave has already reached will move at the same speed c. But inside this area, the crests of the electromagnetic wave will indeed move faster than the speed of light, as if overtaking the imaginary boundary of the area already covered by the oscillations. The disturbance itself will not go beyond this boundary. And there is no contradiction with the theory of relativity here, because the speed of wave propagation in the medium is responsible for the transfer of energy, momentum, information, or whatever else. Roughly speaking, the speed of photons themselves. Okay, it seems like we've sorted that out, and now let's see what happens to light in a medium in cases where our model doesn't work. For example, one of our key assumptions was the assumption of the presence of a restoring force acting on charged particles. That is, the assumption that these particles are somehow bound in the medium. But this is not always the case. Indeed, in metals, for example, there is a so-called electron gas of conditionally free electrons. And for these charged particles, our assumption of the presence of a restoring force and the formulas derived from this assumption will no longer work. The electrons of the electron gas will freely oscillate under the action of the field of the incident electromagnetic wave, and the intensity of the secondary waves generated by these oscillations will be much higher. And here comes into play a consideration that we didn't use before out of necessity. The fact is that the secondary transmitted and reflected waves also have their own energy, and it's obvious that this energy simply can't come from anywhere else but from the energy of the incident wave. In fact, the electromagnetic wave, after interacting with the first layer of electrons in the metal, will expend all its energy on exciting the electrons, which will then convert into the energy of the secondary transmitted and reflected waves. The same will happen for the next layer of electrons. The energy of the secondary transmitted wave emitted by the previous layer will be completely absorbed and re-emitted by these electrons, once again breaking down into transmitted and reflected waves. The same will occur with this tertiary transmitted wave when it encounters the next layer of electrons. In other words, the electromagnetic wave will not be able to penetrate the metal to any significant depth and will completely reflect off its surface. This is why metals are excellent reflectors and shine brightly, and why mirrors are made from polished metals, reflecting all incident light. Our second assumption was that all the energy of the oscillatory motion of the charged particle excited by the field of the incident wave would transfer into the energy of the secondary electromagnetic waves. However, strictly speaking, this is not the case. Part of this energy will be absorbed by the substance, converting into its thermal energy. Essentially similar to how the kinetic energy of a swinging pendulum is gradually absorbed by the resistance forces of the medium, known as dissipative forces, and the oscillations decay over time. Indeed, this is why light penetrates only to a certain depth, even in transparent media. In seawater, for example, it practically does not penetrate deeper than 1.5 kilometers. And yet another case in which our model doesn't work is when the frequency of the incident light wave is close to the resonant frequency of oscillations of the charged particles, be it, I repeat, electrons in atoms, ions, or something else. In this case, the energy of the light wave is also practically completely absorbed by the substance, converting into the energy of particle oscillations. This is the so-called mechanism of resonant absorption. And this is precisely why different substances can be transparent to some electromagnetic waves and opaque to others. For example, glass, transparent to visible light, is practically opaque to ultraviolet, and so on. It's important to understand that the same material can contain various types of charged particles that interact with light in completely different ways. So the transparency spectral curve of the material may have, and indeed does have in practice, a rather complex shape. And with that, I suggest we conclude for today. Don't forget to hit the like button if you enjoyed the video and subscribe to the channel so you don't miss anything interesting. Goodbye, and until next time.